Hello. I'm answering a question that appeared in my Discord today. And someone asked whether a single tree data structure or multiple trees is more efficient. They didn't really give the function that it's more efficient for, but so I'll try to answer this more generally. I don't think there'll be much contention though, because the answer's quite clear cut. So firstly, trees are typically used for faster lookups, and the reason this is faster than other methods is, let's say we're using a list, and we have the nodes that I'm drawing. Okay, and you want to find two in this data structure. Then it will check this. It'll go, no, that's not two. Check that. No, that's not two. That's not two. That's not two. This is two. Ta-da. And then it'll be like, yes, this is contained in the data structure, or it might return the location that it's found it in which case this will be index 4, as this lists are typically 0 based. Okay, whereas if we had a tree, then it would be like this. In fact, I can't remember the exact numbers I used. I think it was this. So we'll make a balanced tree containing these elements. The median is 7. Then we'll have then we've got 5, 9, 1. Wait. No, that needs to be 2 here. Aha. 2, 1, 5. That's 9. Then in this example, to get basically we're considering worst case here. So in this example, we'll try and find 1. 1 only takes 2 steps. So you start the 7. 7 is not 1. 2 is not 1. 1. So that's took only like 3 checks. Whereas before in the list you had to do at most 5 checks. And it turns out that lookups in a tree are they are log n of the size of the tree. So this means worst case scenario in a balanced binary tree, you're doing log n lookups, whereas worst case in our list before we had n lookups. So we say the time complexity is O of n for the list and O of log n for the tree. Okay, so now back to the original question. They were asking whether multiple trees or a single tree is optimal. And if we're assuming this is lookup based, there are like fancy heaps, like binomial heaps and Fibonacci heaps, which do kind of use the multiple tree idea, but they do it in order to have faster writes. And as this is quite a simple video, we'll only consider the lookups. And because those are very complicated data structures and they're also talking about trees, not heaps, so we won't think about that. So I'll consider multiple trees versus a single tree. So we'll have some more elements. We'll consider all like this. We'll consider basically numbers 1 to 10. Okay. And we'll construct a single tree. So the median value is 5. Then we'll do 3, 7, 6, 8. Okay, that's not perfect. I think we want to make this element 8. It's quite hard to just construct these immediately. 7, 9, 10, 3, that will be 4, that's 2, that's 1. Yeah, I think that's as balanced as you can make it for only 10 elements. I think you have to make it power 2 for it to like be a nice full binary tree, but this is as balanced as we can make it. And then if we had multiple trees, so we'll consider 2 trees. just to make it easier. So in fact, let's do 3 trees, and then I can easily construct it. So we'll have a tree only containing 5, and we'll construct the other trees like this. Okay, so they are 3 trees. Okay, so now let's consider the, checking whether something exists in each tree. So if we try and check, so let's check 1 in these examples. So that is not 1, that is not 1, that is not 1, that is 1. So that's 4 lookups. That is not 1. Okay, 1 is actually the same in both examples. Let's come up with a better number. Let's go with 10. I think 10 is the most exaggerated one. So that's 4. No, we're going right on 10. There we go, because 10 is bigger each time. So that's how the binary tree simplifies things, as you go in the direction. So all of these elements are less than 5. All of these are greater than 5. So we go right, and then you repeat that logic. So this is 4 lookups. Here, that is not 10. That is not 10. But we still got to check here, because it could be here. Because all these are bigger ones. That is not 10. So you've got 3 lookups so far. That is not 10. That is not 10. That is not 10. You've got 6 lookups. So the multiple trees thing, you're having to do linear searches for the on the top elements. So it's linear in the number of trees. And then within each tree, you're doing the log lookups that we were doing for our single tree up here. And basically, so this is O of log n here, whereas this algorithm is O of m, where m is number of trees, and log n, where n is number in each tree. This approximates a bit, because this n is kind of assuming each tree is of the same size, which it was in our example. But if we consider that version, that I kind of need to, I need to write the time complexity, and you can see that also m times n in this example, so we call this n1, is equal to n2. We call that n2, so we can write this as that. And if you're familiar with maths, then you know that a logarithm grows much slower than linear, which is kind of the mathsy way of this example I showed above. So that's kind of the idea. Obviously, if we're considering how quickly you can build up this data structure, the cost of ensuring a tree remains balanced can be quite expensive on writes. Whereas it is possible with like clever heap stuff like binomial heaps, Fibonacci heaps, to make the time complexity of this much lower for like building the data structure. So if you've got a very write intensive task, you might end up opting for the multiple tree approach, but that's quite complicated. And in the example given, I think it was a more read constrained problem. And also generally, the kind of things you use trees for tend to be lookup heavy and not so much write heavy, like most of the time. So this is a good rule of thumb. And yeah, hope this video helped. Bye.